Morning, everyone. We are going to be looking at our next chapter, which is chapter 6.2. In particular, we're going to, this deals with an application of integration called volumes of revolution. We are going to be doing volumes of revolution, but there are two different ways in which you can find what are called volumes of revolution. One of them, the one we're going to be dealing with today and tomorrow as well, I strongly suspect. It's called the disk method. It also is called, it's also called the washer method. So if you want to go searching for, terms so you can get some examples or videos or whatever, disk method, washer method. So let's show you what the problem is. Suppose you have a function y equals f of x, and you're looking at it from x equals a to x equals b, and you're going to take this curve and you're going to rotate it about the x-axis. So can you imagine this black line being rotated about the x-axis? I have in Canvas some animations that other people have done where you can see that happening. And since I don't have the ability to do that, I'm going to do a very, very poor example of what that might look like. Just going to go in and go bump. Hey, I've done worse. Now, can you imagine this shape, this piece here, being rotated about the x-axis? Can you see that this would be a kind of side-on view? But really, what you've got, don't you have a bell shape? And the volume of revolution is the volume of this three-dimensional shape that is generated by taking a y equals f of x and rotating that shape about the x-axis. Now, I did this with the other class, so I think, to be fair, I should try and do it with you. I'm going to create the formula for how that worked. So, imagine that you took a random vertical slice that looked like this. If you did that, this piece here, right? So you're getting your knife and you're cutting it, right? Wouldn't this piece here basically be a circular disc, hence the name, the disk method? And right in the center, coming out at you, wouldn't that be the x-axis? So for this random slice, let's say it's at position x. This width, we'll call it delta x. So delta x is, think of it like a coin, right? Like a disc. It's delta x wide. Won't the radius of this disc be the distance from here to here? Well, at position x, won't that be f of x? So this disc has a volume, and it's pi times the radius squared times the height. It's a little baby rectangle. Not rectangle, a little baby cylinder. And it's pi f of x squared delta x. And then what you imagine doing is making these little slices infinitely small, but starting at one side and cutting your way all the way to the end. If you added up all these discs, wouldn't that be the volume of the ship? And this is one of the discs. And if you add them all up, you get an integral from a to b of pi f of x squared dx. So do you see how this formula generated the formula that we're going to use? So we now have a formula. If you want to rotate a single curve about the x-axis, you will use this formula. There we go. So let's do an example of that. Suppose I wanted to take y equals the square root of 2x plus 1, which basically looks like that. And I'd like to rotate it about the x-axis, and I'd like to do it from x equals 0 to 4. So that would be 0 here, and you can imagine this is 4. So I'm going to take this shape, and if I rotated that about the x-axis, can you imagine you might get a shape that looks a bit like that? Imagine what that would look 3D. To me, it reminds me of an acorn or a bullet, right? That kind of shape. Right, how do we find the volume of this particular shape? It's the integral from the start to the finish of pi, the function squared dx. Now what I typically do is pull the pi out and go from 0 to 4. Since that's a constant, you can pull it out of the integration. What that means is that we'll just do a normal integration, and if it ends up being 7/11ths, the final answer is 7/11ths pi. I found that if you keep the pi in here, it just gets in the way of everything and it messes up your whole process. So if you just pull it out, you can ignore it and just tag it at the end. Now in this case, the function is the square root of 2x plus 1 squared. Well, that's going to get me the integral from 0 to 4. It's not meant to be a trick question here. What is the square root of 2x plus 1 after you square it?
2x plus 1?
See how nice? Because you might have been a little bit worried you were going to have to deal with some really ugly U subs or something, and you know, and sometimes you will, but not this case, right? Came out really clean. So power rule, 1 becomes 1x, evaluated at 0 and at 4, and then multiply it by pi. Plug in 4, you get 16 plus 4. Take away a whole load of nothings. pi. Kind of cool? Single function being rotated about the x-axis. That's your guy. In order to do the next question, we'll have to do a little side issue work. It's not uncommon that you're going to have to integrate sine squared or cos squared. But those guys are no use in that format. You can't really integrate sine squared. You can't really integrate cos squared, right? Ain't going to happen. So we need to turn them into something else using a trig identity. And I'll give you a clue to what I'm looking for. Sine squared x can be written as a half of something, and so can cos squared x. Anybody remember what the expression sine squared x is equal to? It's a trig identity from 142. Anyone got it? Okay, here it goes. It's 1 plus the cosine of 2x, and this is 1 take away the sine of 2x. So I'm assuming that you've got lots of little cheat sheets around, right? Little tables and bits of paper with things written in it. You might want to put that on one of them, maybe put everything together in a couple of sheets. You also may want to keep some of your standard angles handy, right? What's the sine of 1/3 pi, that kind of thing, because that has appeared now and again, hasn't it, over the last few days? Just having something like that close at hand will just speed things up. It'll stop you having this interruption where you have to go and find something, because then when you come back, you've forgotten what the process was because you kind of get distracted. So here's the guy we're going to do. We're going to do y equals cosine x.
Your sine squared x, shouldn't that be a 1 minus cosine 2x?
Oh God, yes. Thank you. Wow, that was terrible. Yes. I did it right with the other class, so go figure. So y equals cosine x is going to be the guy. So y equals cosine x is this guy. And we're going to do it from 0 to pi upon 2. So if I did rotate that shape, it would probably look something like this. Yeah, they all look kind of like acorns or bullets, I guess. Right, let's figure out what the answer should be, right? Well, the volume is the integral from 0 to pi upon 2. Pi, the function, squared dx. So it's going to be the integral from 0 to pi upon 2. Pull the pi out, cos squared x, which is the integral from 0 to pi upon 2 of 1/2 1 plus the cosine of 2x dx. Right, the next line is not necessary, it's more cosmetic than anything, but this is how I do things. Do you know that half is just going to be a pain in the butt, so I'm going to pull it out. Because to me, that's just a little bit more elegant. Isn't it less hassle when you have to have fractions of things already floating around? Integrate 1, you get x. I want to find the antiderivative of cosine 2x. How will I go about doing that? Cosine of 2x. How am I going to get its antiderivative? What method will I use?
Don't you just use the chain rule?
Well, chain rule, if it's a chain rule I think you mean, then you're talking differentiation, which means you're going to have a times 2. But if you're using that term in another way, it may still be correct. So maybe I should phrase, what is the answer? And then I'll know. What is the answer to the antiderivative? Last chance. It's that guy. What's the method? How about u sub u equals 2x? Can you trust me? Eventually, that's what you get. Now, in this case here, then, it's going to be 1/2 pi. Plug in pi upon 2. Well, that gets you 1/2 sine of 2 lots of half is pi. Take away nothing, sine of nothing, take away the whole of the nothings. What's the exact value for the sine of pi?
0.
Agreed? Right, 0. So basically, that's all we get. And that times that is quite a pretty looking answer, isn't it? Pi squared over 4. Could be a lot uglier. But a lot of the terms ended up being 0, which was kind of nice. Any questions about that? What's coming to my mind is that you need to start getting up to speed on being able to look at trig functions and realizing how you're going to integrate them. Now, right now we have power rule for things like x squared and x cubed, and we have u-subs, and we have standard integrals. It has to be one of those three things, right? Every integral's got to be a power rule, one of the standard integrals, or a u-sub. And so we need to brush up on it. So far, so good? Happy? Okay. Let's see where else we're going to go. Scrolling down some more of these fellas. Right. Speak a little bit harder. Suppose I have y equals x cubed, and I have y equals x, and I want to do it from x equals 0 to x equals 1. And I want to rotate it about the usual x-axis. Now, if you do y equals x cubed, it looks like this. If you do y equals square root of x, it looks like this. And the little banana shape is going to be the fella that you rotate. Now, this is different in quite one major way that's really important. Do you see in this question, the area or the little vertical strip that I'm cutting, do you see that that's actually made up of two different curves, a top bit and a bottom bit? Now, in this situation, the volume formula gets adapted. It's pi. So what you need to do here is, can you imagine this slice? If I sliced it this way, wouldn't you get a donut shape looking thing? And do you see that the area of this donut is big circle, take away little circle? That's what this is. And then the dx and the rest. So in this question, it's going to be the integral from 0 to 1. Stick out the pi. In this question then, the big is the top guy and the small is the bottom guy. So the big guy goes here, the little guy goes here. So the one that's tallest and the one that's smallest. So in this case, it's going to be x squared, take away x cubed squared dx. You see, that's a little bit more difficult now. You've got a little bit more work because it's the area between two curves that's being rotated. And notice it's f of x squared take away g of x squared. So let's see what that looks like. X squared take away x to the 6. Right. How am I going to, what rule am I going to use to integrate this fella?
Power rule.
Okay. So it's going to be 1/3 x cubed, subtract 1/7 x to the 7, evaluated at 0 and at 1. If you plug in 1, you get a third, take away a 7th. If you plug in 0, you just get a whole load of zeros. 1/3 take away 1/7, that's 7, take away 3, it's 4/21s. There's your answer. 4/21.
Can't see your paper, sir.
That's the bottom. 4/21 pi. So rotating a single curve is pi f of x squared. Rotating the area between two curves is pi f of x squared, take away g of x squared. Let's try this fella. Y equals e to the half x. We're going to do it from 0 to 2. And it's still going to be about the x-axis. Right, if you sketch y equals e to the half x, it's just a boring curve. There's 0. Here is 2. There is the region. Here's my typical vertical rectangle, right, at position x. In this case then, won't the volume just be pi, the integral from 0 to 2, f of x squared dx? Would you agree it's just a single curve again, right? Sometimes they're 2, sometimes they're 1. I think when you draw the picture, it kind of helps me to see what the heck it's doing. Now, what we're going to do here, and the reason I chose this one, is just some algebra issue. If you take e to the power of half x and you square it, what power of e does that become? Andrew, if you're saying something, I can't hear it.
No, sir, just thinking.
Okay,
I think that'd just be e to the x.
that's it. You can think of it in a couple of ways. Couldn't you think of it as meaning e to the half x times another e to the half x? And isn't the rule then that you add them together? And 2 halves get you 1x? That'd be one way of looking at it. Isn't there a rule that says if you raise something to a power, you multiply the exponents? So 1/2 x times 2 just get you x. It's a different way of approaching it. This guy here is actually pretty easy to do, would you agree? E to the pi, take away e to the 0, which is 1. E to the pi, e to the 0, which is 1. And that's considered the right answer.
Where
Yes.
did you get e to the pi?
Oh. Now I got e squared minus 1.
It makes me much more comfortable.
I don't know where pi was coming from. Probably my brain's still thinking of trig.
Is that the final answer?
Yeah, e squared minus 1 pi.
It's kinda
I'm pretty
easy.
sure that WebAssign would take either of those two versions because it's the same thing, isn't it? Here's a visual one. We want to rotate the region between y equals 2x and y equals x squared. And we want to rotate it about the x-axis. So I'll do my little vertical rectangle to kind of represent one's vertical cut. We know that the volume is from some start number to some finish number, a pi, f of x squared, take away g of x squared. Well, I'm pretty sure I know that guy. As you agree, zero's kind of obvious, you can see it. What I'm not so clear about is that guy. But I need to know it, because isn't he the second number? Can you have a guesstimate, or can you at least tell me how you would find the second x value, the one that goes here?
It should be 2.
It should be 2. Do you want to share with the rest of us how you figured that out?
Because the only numbers that I can think of that would square and then also multiply by 2 would be 2, and they both equal 4.
Oh, I got you. So you were just, you know, scanning through obvious numbers, and that's the only one that came out that worked. That kind of process. Yeah, worked well. If you wanted to do it algebraically, aren't you always looking for when is the first equation equal to the second? As long as it's a whole number, do you know in Desmos you could probably read off the answer? You'd be able to see it, it looks like a 2. But, you know, and maybe it's going to be square root of 2 one day. So first curve equals the second. Subtract 2x from both sides. Take out x as a common factor. And can you see that's, excuse me, isn't that the formal way of finding it? And that method is probably only going to be really useful if the answer is not a nice number like 1, 2, 3, 4, right? If it's some number like square root of 3, you're not be able to get it as an exact value by just eyeballing it. So I'm going to pull out the pi. Now I have a decision to make. One of these two functions, either the 2x or the x squared, is going to go first. And then the other one, whatever it is going to go second.
That'd be the 2x, right?
I agree. And that makes the x squared second. You want to share why you figured it out that way? Why it was the way you said? Why is the first one 2x and the second one x squared? How can you visually tell that?
2x looks like the base of it, the top of it.
Yeah. Is it the straight line on the top and the curve in the bottom? Now this guy here becomes pi, the integral from 0 to 2 of 4x squared, take away x to the 4. And I'm just going to dot that one. Wouldn't you agree it's just a power rule and you can do power rules yourself? Perchance, maybe it could happen. Can you imagine a situation where you just switched them by mistake? You thought that one should have gone first and this one was going second. You would get a numerical answer. Have you any idea what that numerical answer? Can we pretend that this is 42 pi, right? If you do it the right way, it's going to be 42 pi. If the only thing you did was switch them, what would that answer probably be?
Negative 42 pi.
And since this is a physical volume, right, a real life object in 3D, shouldn't the answer always be positive? So if you do it the wrong way round, aren't you going to know because a negative number comes out in your answer? And secondly, if it is a negative number, don't you also know what the right positive number is, provided that's the only thing you did wrong? Won't it be 42 pi? So if you do it the wrong way round and it's negative 7 pi, don't you know the correct answer is positive 7 pi? That probably would be a good help if you had to spend 10 minutes to do it. You probably don't want to just go back and start again just for the fact that you switch places on two guys. You could probably figure out the next time to do it in the right order so you won't have that issue. Could you ever get 0 in a volume of revolution question?
I don't think so.
No, because wouldn't that mean that the object isn't there?
Yeah, it has no volume.
It has no volume. So you know that you're never going to get 0 and that it must be positive. They're quite helpful clues, aren't they? And the way that these are constructed, shouldn't there be a pi at the end? Because I've seen it in a really complicated question. You're that focused on the numbers, especially me. And can you imagine a situation where you just dropped the pi halfway through and you forgot to continue it? So if you ever see the answer 42, aren't you going to think, there's something missing there? There better be a pi, right? Whatever it is. So negatives aren't any good. Pi's need to be there, must be positive, and you'll never get 0. Right, that's just some of the general truths to how this works.
I have a question.
Yes.
So if the on the interval that we're looking at, if both the functions occupy the same exact line,
Well, that would mean there'd be the same equation, wouldn't it?
well, like maybe two different equations, but on a certain interval, it's occupying the same exact space, if that makes sense.
Yes, in which case the volume would be 0.
Okay.
Because, well, would it be 0? Yes, the area between them would be 0, so therefore the volume would be 0. I think it's quite difficult to get a function that matches another function, but only in part of its world. I mean, okay. I can't off the top of my head think of one, except a piecewise function.
Okay.
And it ain't going to happen in any of the homework questions, so we're pretty safe at assuming that it'll never be 0.
Okay, cool.
Mr. Robertson, for the last problem, request insertion of the interval for like the number answer. Because that part is confusing me, like the 2 to 0 on the last problem, I think it was.
I'm trying to find the darn thing now. Where is my order? Right, this is not it. That was the second last one. Oh, it was this one, right? Okay, here we go. Right, so you were saying about inserting?
Yes, at this point, you need to, you would as a student put in the interval, right?
Oh, you would still have to keep working. I just stopped there because it was, you know, we've done all the hard stuff. So if you wanted to continue to see what the rest would look like, wouldn't you have to do that? Then you'd have to evaluate it at x equals 0 and x equals 2, and then stick a pi at the end. So you can imagine 2 going in, then 0 going in. So what's that? 2, 4, 8, 32 thirds. 2, 4, 8, 16, 32 fifths.
Yeah, I was just missing a step.
Yeah, I have no idea what that is, but isn't that what calculators are for? You know, you'll get some. Yeah, do not be too concerned if you end up with 17 107ths pi or something. I can imagine some really weird, you know, polynomials coming out with some really ugly fractions. But at least it'll be something pi, right? That's something you can't avoid. Now, see what I can find here. Yeah. I'll have to do this again. That's what I want. Okay. Now I know what I want. I will draw it again. Right. So that's the question. We're going to take that triangle and rotate it about the x-axis and find the volume of the shape that we would get. Now, if you imagine this shape being rotated, can you imagine it would probably look like that, wouldn't it? Can you see this bit here is going to generate a circular hole? Well, actually, that'll come to a point, but well, it'll cut off at the hole at the bottom, right? So it will be that one, right? And I don't know if that cross section helps or not. So that's the guy we're going to find the volume for. Kind of interesting shape. So let's see if we can set up, based on the information that is here, what the integral for its volume should be. What are the limits of the x's based on what you can see in this picture? The x's start where and finish where on this picture?
0 to 2.
Great. Right. From here to here. Now, when I do my little vertical rectangle thing, you see this thing doesn't go all the way down to the x-axis. Isn't this thing really a start and a finish? Is a top and a bottom? So it should be pi, some function squared, take away a different function squared. So we should be looking at that situation, right? So it's going to be the integral from 0 to 2, stick the pi out. Looking at my picture, don't you always do the top one as f of x and the bottom one as g of x? Well, the top one is 2x plus 3 squared. Take away. What is the bottom guy?
Y equals 3.
You may have said something, but it was so faint I didn't catch it.
Y equals 3.
Agreed. So don't you just plug in 3 and square it? So there's an example where one of the two functions was actually just a horizontal line, which makes it only a number. So that's basically y equals 3, or if you prefer, g of x equals 3. So 3 gets squared. Now this is a practical issue. If you want to find the integral of this, shouldn't you probably FOIL it all out and collect like terms before you start doing anything? Because if you leave it like that, you're going to have problems. So I have 4x squared plus 12x plus 9, take away 9. Which means that we are now left with that guy. Are we cool with that question and how it was approached? Can I say ... and you know how to finish it off from here?
Yes, sir.
Just another big ugly power roll with whatever. So for the last question, we are going to find the formula for the volume of a sphere. Does anybody know what the volume of a sphere radius r is? It's one of those formulas you don't really use much. It'd be nice if you knew it, but you know, you may not.
Isn't it x squared plus y squared equals r squared?
Oh, that's the equation of the circle. which I will be using. But the formula for the volume of a sphere is 4/3 pi r cubed. Does that ring any bells for some of you? The volume of a sphere is 4/3 pi r cubed. And you might think, where did that come from? Why is it 4/3, right? It could be 6/7, you know? Why is there even a pi there, you know? What's going on? Well, let's prove it to you. I am going to construct a circle whose center is the origin and whose radius is r, which brings us to what you said earlier. Now, if you rearrange this equation, doesn't that tell you that y squared equals r squared take away x squared? And then if you turn it into y equals, you get this guy. And I want you to think of that as being your f of x. And I also want you to think of the thing that's called r squared here. Well, you think of that as a constant. It's just like 5 squared or 10 squared, right? It is just a number. Now, if you imagine what that circle would look like, at least the top half would look like that, which is what this one is. If you took that and you rotated it in the x-axis, wouldn't this point here be negative r, and this point would be plus r, because you imagine the whole circle, that would be the radius, right? 0 to r. Now, if you take that shape and you rotate it in the x-axis, don't you make a sphere? A half a circle rotated in the x-axis. So the volume of this sphere is basically going to be this guy, right? Rotated in the x-axis. So it's going to be the integral from a start value of -3 to a finish of +3 pi f of x squared dx. It's going to be the integral from -3 to 3, stick the pi out there. This fella squared. I guess I'll put it in. This is kind of nice. Isn't the square root of r squared negative x squared all squared just r squared take away x squared? Don't those two processes essentially cancel each other out? Now, keep in mind that r squared is just a constant. It's like 5 squared. Right? Keep that in mind. So here we go. If you take any number and you integrate it, you find its antiderivative, are you happy that you get r squared x? Like 5 would get me 5x and 5 squared x would get me 5 squared x. And isn't x cubed the good old power rule that we're all familiar with? And we are going to evaluate this at x equals -r to x equals plus r. And when we're finished, we'll stick a pi on it. So I'm going to go over here now. If you plug r in here, you're going to get r squared times r, take away 1/3 r cubed. Subtract. If you now plug -r in here, you're going to get r squared times -r, subtract 1/3 -r cubed. Do you see I'm replacing the x with r and then the x with -r? X with r, x with -r. This guy is r cubed, take away 1/3 r cubed, minus. This fella is -r cubed, and this fella is plus, I've tried to keep track of all the cubes here, that guy. Isn't 1 r cubed take away 1/3 r cubed 2/3 r cubed? Isn't -1 r cubed add 1/3 r cubed going to get you -2/3 r cubed? 2/3 r cubed add 2/3 more r cubed gets me 4/3 r cubed. So the volume of a sphere is 4/3 pi r cubed. Do you know, if you look at a formula sheet, won't you find formulas for the volume of a cylinder, the volume of a cone, the volume of a sphere, can't think of any, the volume of an ellipse, and some others? Do you know all those formulas came from using this process? So if you want to create, if you want to have, if you're just interested from doing it from scratch, couldn't you create the volume of all sorts of things? Give you an example. See, if you want a cone, don't you just take a straight line and rotate it about the x-axis? Wouldn't that get you a cone? If you want a cylinder, don't you just take a horizontal line, starting and finish wherever you felt like, and rotate that about the x-axis? So you can get lots of shapes. You can even get the volume of shapes that are much more stranger than that. Didn't we find the volume of a shape which is essentially a cylinder with a hole cut in the middle? A cylindrical hole?